Okay, what we're going to do in this section is look at the mathematics of finance. And there's a lot of really interesting, really fun, cool things that you can do with numbers and money. So we're just going to go through and work some examples out here of different ways to use it. And the primary equation we're going to be working with throughout most of this section is going to be some form of this guy right here. It won't always look like this, but the shape of this equation will always be the same. So let's just dig in. By the way, P is the principal invested. That's the amount of money you're going to put towards your savings or your investment. R is the interest rate that you're going to earn. And N is the investment after however many years. Okay, so let's just say, for example, that Madigan invests $500 at 7% interest compounded annually. Find the value of her investment 10 years later. So with Madigan, what we're going to do is we're going to look for P, and P is going to be equal to $500. Okay, the interest rate for Madigan is going to be 0.07 as a decimal. And the N part is the number of years that it's going to take to fulfill this requirement. And it just, here's your guys. So basically, what you're going to have is the amount of money that you have after 10 years. And so our amount after 10 years, if you want to note it that way, would be 500 times 1 plus 0.07 to the 10th power. And you're just going to punch all that into your calculator. And when you do that, you end up with $983 and 58 cents. Okay, and so that's how you use this, like this compound interest formula. And this is the simple way to do compound interest, and that's how much money you would grow. So your money would double over a 10-year period, almost double over a 10-year period, without you touching it at all or adding to it, just letting it ride on 7% interest. So let's suppose that Rowan invests $500 at 9% annual interest compounded monthly. And so that's going to change this base equation just a little bit. It's still, now watch, the shape is going to be the same, but now it's going to be A equals the principal, so that part's the same, times 1 plus, so this part's the same, but now we're going to do whatever that interest rate is divided by the number of times that we compound something. That's what the K is, the compounding part. And then up here on the top, the N, instead of just being over years in general, is going to be the number of times total that we compound the interest. Okay, so this compounded monthly part right down here that we're looking at, this is just going to make the K be equal to 12. And so when we sort this guy out, then when we set him up, we're going to look at the principal is equal to 500. So that part doesn't change. We're looking at the interest rate equaling 0.09. We're looking now at K equaling 12, and we're looking at the time T to be equal to 5. So again, we've got everything we need. We can just substitute all the stuff in. So if you want to look at your function, and I'll note it another way, A5, the amount after 5 years. So this is a couple different ways to note your amount of money you're going to earn back. So this is going to be 500 times 1 plus 0.09 divided by 12, and then up in the exponent is going to be 12 times 5. Okay, and so that's this guy. And when you punch all of this into your calculator, and be careful how you do it, now you've got a fraction in there, but when you punch all this into your calculator, you should end up with $782.84. And so that's how you're going to use the compounding monthly. Quarterly, if you're going to compound quarterly, that would be 4. If you compound semi-annually, that would be 2. And so there's going to be clues in there in the problem setup as to what your K value will be. Okay, now on to Marin. She's got $500 to invest at 9% annual interest, compounded monthly. How long will it take for her investment to grow to $3,000? Now they've given us a lot of information, but they have not given us our T. And I've got the equation up here for you again. And notice it's exactly like the one we used on our very last example. And so let's just go through and just label what we know. We know that P is going to be equal to $500. I know that my interest rate is going to be 0.09. I know that the amount that I'm going to receive when I get done with my investing is $3,000. And I know that I'm compounding stuff monthly, so that K is going to be equal to 12. And let's just remember that this guy's also $500. Okay, so my setup then gives me everything except T. So go ahead and substitute all the things in that you need, and we'll see if we can't sort out how to get to T. And T is located as an exponent, so this may or may not be a little bit tricky. We'll see. So I've got this set up right here. 1 plus 0.09 divided by 12, and then up here in the exponent, 12 times T. Okay, so there's my setup for this guy. And what do you do? Well, one of the easiest things to do is to graph the left side and the right side and find a point of intersection. And so when you do that, it'll show you exactly what T needs to be. We can also sort this out algebraically, so one can confirm the other. And when we do the algebraic part, you're going to divide both sides by 500. So what you end up with is 6 equals, and then we can do this guy right here in our calculator. Ooh, that's a bad circle. We can do this guy in our calculator and get a decimal. And so when you do that, that's going to be 1.0075 to the K. Whoops, K in this case is 12. Okay. The problem now is that with the T up there in that exponent, we can't get it out. So what we can do is rewrite this as a logarithm. And remember, a logarithm is equal to its exponent. So in this case, we would have a log of base 1.0075 of 6 is equal to 12t. And if you want to punch this into your calculator, if your calculator will let you do logs of different bases, you can just punch in the right-hand side and divide by 12. If it doesn't, then you'll need to use a change of base formula. So we would look at the natural log of 6 divided by the natural log of 1.0075. That looks like a 9. And that would be equal to 12t. So again, you can punch your natural logs in your calculator very easily. And then whatever you get on either one of these, we have to divide both sides by 12 to get the t all alone. So no matter what you do, you're going to end up dividing by 12. So the ultimate thing that we're going to end up here with is that t is equal to 19.983 years. Okay, so here's a typical word problem that you can see that wanders around in these financial parts, and that is this: that Jasmine has $500 to invest, and she wants to double her money in 10 years. So what annual interest rate, compounded quarterly, is required to double her money in 10 years? And then again, what about doubling in 5? So we don't know what the R value is in this case. No problem. We can write down what we know, keeping in mind that we're working with the equation P times 1 plus the rate over the K, and then K times T. This is our equation that we're working with. So let's go ahead and set up what we know. We know that A is going to be double 500. So it's going to be $1,000. We know that P is going to be equal to $500. We know that T, for the first part, is going to be 10. We can do this again with 5 in just a moment. The rate is what we're unsure of, and the K is quarterly, which means 4. So the setup then on this guy is not too bad. It's going to be 1,000 equals 500 times 1 plus the rate we don't know divided by 4, and then 4 times 10. And to clean this up a little bit, divide both sides by 500. So 2 is equal to 1 plus the rate over 4 to the 40th power. All right. Now again, how do you deal, with this? Well, one thing that you can do is you can graph the left side and graph the right side and find a point of intersection, and that'll allow you to find out exactly where the solution is for the number of years that works. The other thing that we can do is we can try and get that R out from inside the equation. And notice that right here, I've got a 40 for my exponent. So I can take a 40th root of both sides, which is really going to be gross looking, but it's totally doable in this day and age. So we would just take a 40th root over here, or even better, let's do this. Let's raise both sides to the 1/40th power, because if we do that, the 40s will go away. So what I end up with on the left is 2 to the 1/40th power equals 1 plus the rate divided by 4. And so you can punch into your calculator 2 to the 1/40th power. And that's going to be 1.0175. Subtract 1 from both sides. And multiply both sides by 4. And so you end up with R equals 0.0699, which tells us that our rate is 6.99%. Okay, so continuously compounded interest is just a little bit different, not too different, but the shape is the same as all the other ones. The shape has not changed at all, but some of our coefficients have. And with interest that's compounded continuously, we're now going to be working with E, and E is like pi. It's a constant. It never changes, and so you can punch it into your calculator. But E is roughly equivalent to 2.17828, and so this is what E is. Okay, and if I've got an investment and I've got $500 at 8.5% annual interest, compounded continuously, find the value after 1 year, 3 year, 8 years, and 45 years. So the amount I don't know, but I know that my P is going to be $500. I know that my rate is 8.5% or 0.085. Okay? Find the value of the investment. So we just set it up following this formula. My amount after 1 year, I'll show it a different way again, is going to be equal to 500 times e to the 0.085 power times 1. And so you would just punch that into your calculator, and when you do that, 500 you get $544. Whoops, $544.36. Okay, not a hard thing to do. So, what about after 3 years? Same setup. 500 times e to the 0.085 power, now times 3 though, because that's my time. And so what's that going to equal? Well, you just punch it into your calculator again. And this guy's going to end up being $645.23. Well, what about after 8 years? Same setup. Now instead of times 3, it'll be times 8. So punch that into your calculator. And this one, after 8 years, your money is almost doubled, $986.94. Alright, what about after 45 years? And I'll just, again, show an alternate way of looking at this guy. We'll put the 45 in the parentheses. Again, same setup. Now we're going to multiply by 45. And that's $22,916.40. So that's how you use the continuously compounded interest formula. And it's just fun to kind of play with that and look and dream, hey, what if you had this much money, and what if you could find a continuously compounded account? How great would that be? Okay, we've got the annual percentage yield now. And this comes into play when you are getting a mortgage, or you have a credit card, or even with a different, if you want to compare different banking accounts. And what it does is it takes all the different interest rates, compounded all the different times, and it gives you an equivalent annual percentage yield. In other words, what you're, it gives you a way to compare all these things at once. And the annual percentage yield will narrow it down into like an actual specific interest rate that works across all the different items that you're looking at. So let's say that Reese invests $2,000 with Crab Key Bank at 5.15% annual interest compounded quarterly. What is the equivalent annual percentage yield? And so basically, here's what we want to do. We know that our investment, and again, we're working with the same shape of everything. So P is equal to $2,000, and our rate is equal to 0.0515, and we're compounded quarterly, so K would be equal to 4. This time, though, we're only interested in the time equaling 1. Okay, and so we can set up one side of our equation. 2,000 times 1 plus 0.0515 divided by 4 to the 4th power. And what we're saying is we want to know what the annual interest would be. And so what we're going to do is we're going to work with the most basic form of this equation. Now remember, this form that we just put in, this is for using things that are compounded more than once a year. Okay, and we want to compare this to the one that is compounded just once per year. And so we're going to look at this: 2,000 times 1 plus x, the rate, because that's what we don't know is the rate of yearly. And remember, k now is just 1, and the time is just 1. So this is my setup when I'm trying to look at and investigate which of these guys works best. And so right off the bat, we can divide by the 2000 because it does not have an exponent or anything attached to it. We can't divide those guys with exponents on them because they're tied up with those exponents. And so then what I have on the left, and we can go ahead and work out that problem on the left. 1 plus 0.0515 divided by 4. So on the left I have 1.0, and I'm going to go ahead and write out the whole decimal. 1.01285. And I'm going to list the whole decimal so that I have a good rounding for my final decimal answer. And this is going to be equal to 1 plus x. Okay? And so how do you get that x all by itself? We're going to just take 1.012875 to the fourth and subtract 1. And that will get me my value of x. So punch that into your calculator. And it spits out that x is equal to 0.0525. Well, what does that mean? That means that my annual interest rate that's comparable, so my interest is compounded once a year, is comparable to 5.25%. And that's what my interest would look like if I took the same investment and instead of compounding it quarterly, compounded it annually. So it's not too bad, but it looks just a little bit different. But keep in mind, though, what you're really looking for is you're looking for an interest rate that happens just once per year. Okay, so Rose is now trying to figure out which investment might have a better return. One that has an 8.75% rate of return compounded quarterly, or one that has an 8.7% return compounded monthly. So one is just a little bit higher than the other, and basically what we need to do is we need to look at this as two investments. So, well, they are two investments. I'll work this one in red, and I'll work this bottom guy here in blue, and then we'll compare the end results. So in red, it doesn't really matter how much money we're putting in because it would divide out. Remember on the previous slide, our principal divided out. So the setup on this is going to be the 1 plus 0.0875 divided by 4, okay, to the fourth power, is going to be equal to 1 plus the interest rate. I'll just go ahead and call it R. The second guy then is going to set up with the same way, 1 plus, but not 0.0875, but just 0.087. And this one is compounded monthly, so he's going to be divided by 12, and he's going to be to the 12th power. And he also is going to equal 1 plus the rate. And so now you can just punch all of this into your calculator, so it shouldn't be a terrible thing to do. In red, what you're going to have is 1 plus 0.0875 divided by 4. In red, you're going to have that's not red. You're going to have this guy to the fourth power equals 1 plus R. So all we'll need to do is subtract 1. And when we do that, we get that the rate is equal to 0.9041. And then when we work the same problem now in blue, you have 1.00725 to the 12th power equals 1 plus r. And then do that math and subtract 1. And the rate on this guy is going to be equal to 0.09055. So which one of now one of these is going to work a little bit better than the other, and when you do a little bit of investigating, the interest rate in blue is just a little bit higher than the interest rate in red. So the actual rate of return is going to be that 8.7 compounded monthly. Okay, this is a really fun one to mess with. This is how to determine like the future value of an investment, one that you contribute to on a regular basis, or if you've got a loan of some sort and you contribute to it on a regular basis, how long it'll take to pay off or whatever. And these are your two formulas that you're going to want to use. And it's just really, really interesting. So we're just going to use these formulas. If you need to pause it for a minute to look at them and write them down, do that. But future value is an investment. A present value is a loan. So and we're calling this the value of the annuity. It could be like a mutual fund. It could be a car loan or a mortgage or any kind of thing. So this is a really interesting deal. At the end of each quarter year, so Qatar year, so at the end of each quarter year, so let's just fix it. There's a typo here. This should be quarter. Let's see. At the end of each quarter year, Rowan makes a $500 payment to the Hazelwood Mutual Fund. If his investments earn 7.88% annual interest compounded quarterly, what will be the value of William's annuity in 20 years? And so basically what we're looking at is 4 times a year, William is going to pay $500 into this fund. Well, R is the amount of money that we're going to invest in each period. So in this case, R is going to be 500. My rate is going to be 0.0788. My time is going to be 20. And my compounding period is going to be 4, because this is going to happen 4 times a year. Okay? And so basically what we're going to do is when we set this up, we need to figure out what I is. I is the equal number of R dollars at an interest rate per compounding period. So my I value then is going to be I is equal to the rate divided by the K. So for this guy, I is going to be 0.0788 divided by 4, and 0.0788 divided by 4 is, 1 second while I punch it in, is equal to 0.0197. Okay? And the other thing that I need is N. And N is the total number of compoundings. So N is going to be T times K. So in that case, this is going to be 20 times 4, which is 80. And so now I've got everything that I need to set up the future value of this guy. And what it's going to look like is this. Screw it down, give us a little more room here. 500, my future value, is 500 times, and then 1 plus I to the n. So 1 plus I, which is 0.0197, to the nth power, 80, minus 1, divided by I, which is 0.0197. And now all you do is you just you just punch all this stuff into a calculator and get an answer out. So when we do that, what we end up with is $95,483.39. How cool is that? Alright, so now we've got Rose, who's purchased a new car for $18,500. What are the monthly payments for a 4-year loan with a $2,000 down payment if the annual interest rate is 2.9%? Well, it's going to be the same thing that we just did, the same stuff, but now it's just going to be in a little bit different order. So what we're going to end up with is, we want to know what the payments are. Well, that's the R part, is the number of payments on the present value on a loan. R is your number of payments. The price of the payments. So we don't know what those are going to be. We know that the present value is going to be $18,500. Okay, but we put $2,000 down, so we're going to subtract $2,000 from that. We know that our rate is going to be 0.029. We know that our time is going to be 4. So we still need I and N. And remember that I is going to be the interest rate per compounding period. So if we're doing this monthly, it's going to be the interest rate per compounding period. And so the monthly part of that then is I is going to be 0.029 divided by, I forgot to add K, which is our compounding, 12. So 0.029 divided by 12, and that is going to be 0.0024167. Okay, and the N is going to be the number of compounding periods times the time. So N is going to be 12 times 4, which is 48. So this is going to be my setup for this guy, and I just fill stuff right back into this equation right up here, and so here we go. This is what it's going to look like. My present value, which is 16,500, is equal to the number of payments that I make, that R value, times 1 minus 1 plus I, 0.024167, to the N, negative 48th power. And all of that is over I, which is 0.0024167. And so we know everything except R. So this guy right here, he looks big and scary, but punch him into your calculator, because all he is a decimal. So I'm going to have 16,500 equal to R times, alright, I got a little whoops here, and this should be 0.00. So that should be plus 0.00. And then what I end up with is, when I punch that pink outlined box in, I get 45.26899. I'll go ahead and put one more spot in there just for good rounding purposes, and then just divide both numbers by that, both sides by that number we got, and you end up with a $364.49 payment each month on your car. And so that's how you use the future value one. It's also really handy to have to figure out how much you would spend on a loan.